Good evening, everyone. Welcome to all the attendees for this new webinar from Quantum London. We are very excited tonight to have Michele Mosca, who will give us a talk around quantum computing and risks and readiness. And before we get started, I would like to thank you, everyone from the community, for the feedback from the last session. Incredible, and also we see the numbers of people getting involved, growing and growing. That's fantastic for us. It's very rewarding for myself and Paolo. So we hope to keep this pushing and keep it growing. And just a couple of words about Quantum London for those who are new to this kind of events. So we are a community of people who are trying to understand what is coming when Quantum London is coming our way, what the implications will be, especially from a business perspective, because there are so many great groups out there looking at the technicalities of it. But for us, it's more about understanding how will this change the lives of our businesses. So that's what we're focusing on. And we started in a pub back in 2019, yeah, and with many questions than answers. And we soon realized if we wanted to get a better understanding, we were to bring in some experts from the field, like we're doing tonight, helping us to answer those questions we had and navigate this complex environment. So I will not take much more of your time. I know you're all keen to hear from Michele. And so the title of his talk is Managing Quantum Risk and Opportunity. So we'll be looking at quantum technologies that will bring potential and massive and unpredictable disruption. So it is essential to be ready to seize these opportunities and mitigate these risks. So we will have an overview of the current state of technology readiness and some of the known impacts, and also the approaches of being quantum ready. So topics which are very, very relevant to what we are trying to understand as part of our community. So Michele, without any further ado, I will hand over to you for your talk.
You can't. So I want to talk about being ready for this quantum, this suite of quantum technologies and all their implications. And the important thing to note with quantum computing in particular is, while it's hard to predict, though we're getting better at where the impact will be, it has an astronomically powerful, astronomical potential for impact, as we saw with cryptography, right? A problem that we thought we couldn't solve for thousands of years with all the available computing power on Earth suddenly becomes polytime computable. So where this exponential advantage is possible, it's not a kind of advantage you could ever imagine achieving with any amount of classical technology, but it's a very new kind of capability. So it takes a lot of effort to try to understand where it's applicable. So with anything that's so potentially impactful, but in an unpredictable way, it's hard to prepare, right? So it's a challenge. Unfortunately, we can't avoid that challenge. Step one in quantum readiness is to understand the technologies, what they're capable of at a fundamental level, and where the technology readiness levels are. Once you have that in place, you have to understand, well, what does that mean to me, to my company, to my sector, to my country, right? That's the next step. And again, efforts like this Quantum London initiative is a great way to get familiar, to start answering a lot of these questions and get ready. Once you understand the technology as best as one can, and you figured out what it means to you, then of course you can make a plan to benefit from the from the positive disruptive capabilities. And of course, you must also mitigate any of the threats posed by quantum technologies. So these are the various stages of being quantum ready. And so where are we in the technology, readiness scale? Well, it's already, 5-10 years ago, I could present to you, lovely pictures of great, research projects, right? But in the last 5 to 10 years, they've started to look more like computers and not just science experiments. And now they're really commercially available, like literally commercially available. Of course, they're at this point really research tools versus commercially useful value adding optimization tools, but that can very quickly change. So it's a great physically, of course, these are some sort of implementation of a quantum bit on a chip inside either a large cryostat or a vacuum chamber, and who knows with other potential architectures that might emerge. But that's the two sort of front-running platforms, and there are a couple other opportunities quickly catching up from behind. And new players are continually entering the game. So you see these massive, global multinational companies with amazing resources and ability to attract additional capital, and also some very promising and well-funded startups quickly. In some cases, really catching up to some of the large global players. And this is happening in China as well, who a small number of years ago started investing tens of billions of dollars into this effort, and have been achieving some great results. Again, these are often teams with a long track record of delivering. And new players, or even the last few weeks, new quantum computing companies have entered the space in China. So this is really moving from the research is advancing, the development's advancing, and the commercialization is starting to take hold. And a sign that it's really starting to take hold is that we're not just talking about, and here's my latest attempt at building a qubit. You see entire software stacks built on top of these platforms. They're now recognizing that they really need a full software. They need software to run their computer. They need software to compile the algorithms. They need algorithms, and they need customers for these algorithms, right? So you'll see a number of industry forward-looking companies starting to explore with well-funded, talented teams. What will this mean to the financial sector? What will this mean to Airbus? What does this mean for materials, and so on? So you get large companies starting to explore exactly what we talked about. What does this mean to us? And starting to engage with the vendor landscape. In some cases, even making investments in some of the vendors they find most promising. You have incubators. I volunteered at an incubator in Toronto that nurtures quantum startups. That many of them that have very deep subject matter expertise in one of these verticals, and are now marrying that with deep subject matter expertise in quantum technology. So we have companies dedicated to applications. We have large companies exploring applications for their own use. We have software companies, optimization, right? And if you think, but maybe this is just a fad. Well, at this point in time, major players seem to be doubling down, right? Multi-billion-dollar initiatives around the world, new centers being set up in the United States, which was already a front runner, in Germany, and so on. Audacious, well-funded, coherent projects in Europe, for example, the UK. And so where are we? We've heard about these so-called quantum supremacy or advantage experiments last year, and another one just a few weeks ago. The next big, most important milestone for large-scale, powerful quantum computing is attaining a robust, scalable, logical qubit. And up until 6 months ago, there really wasn't much public talk of when is this really going to happen. And just a few weeks ago, IBM published its own roadmap, which pins that at being in 2023. That's their target date. Other players, they're all working on this, or most of the major players are working on this. IonQ recently released some of its latest experiments moving in that direction. We conducted a survey, which will be public soon, through the Global Risk Institute. We interviewed 44 thought leaders, and here is a histogram of their responses. Again, this is the first time I really hear people publicly, clearly, articulating this is when I think fault tolerance will happen. Beyond the I don't know when, and actually a surprising number are saying maybe even the next year, right? So this green with a 12 means that 12 out of 44 respondents thought it was about less than 30% likely to happen in the next year, right? And again, they didn't choose less than 5% or less than 1%. They chose less than 30%, right? And you have 7 who chose around 50%, and others who chose even more likely in the next year. So we'll see, right? But even within 3 years, 30 out of 44, then we'll publish in January who are these respondents, but these are, globally renowned leaders, diverse group of people with very relevant expertise to make this kind of estimation. 30 out of 44 are in the approximately 50% or higher, even 75 or higher percent category. This realist, and then alongside with IBM's subsequent announcement, this is really feeling real. Now, as we move toward, just to help, and again, many of you have been attending these talks, you're very familiar with the landscape. Some of you aren't. So let me just try to lay out clarify some of the quantum noise you're hearing. I've currently been talking about building a large-scale fault-tolerant quantum computer that can implement any algorithm, right? Any quantum algorithm. Along the way, we're building qubits and so on, and there's other technologies other applications that could be achieved with harnessing quantum systems, such as quantum key distribution networks, point-to-points and small networks, or better quantum sensing, or the first generation of quantum computer, these quantum annealers developed by D-Wave, for example, which solve very special kind of optimization problems, right? And then in very recent years, John Preskill coined the term NISQ, noisy intermediate scale quantum. These are circuit-based quantum computers where we're not doing quantum error correction on them, or at least not large-scale fault-tolerant quantum error correction. But we hope they're big enough that you can start doing interesting things with them. You can get computations done before the quantum errors take over. Okay. So this is an exciting time. In fact, this is, in a sense, what the Google supremacy experiment was using, right? We were able to get, because even if error rate is epsilon, very roughly speaking, you get 1 over epsilon operations in before errors take over. So you can kind of say, well, this is not scalable, the asymptotics are terrible. Sure, but it's exponential in 1 over epsilon. If you find the right algorithm, the kind of power you're harnessing is exponential in 1 over epsilon. So the hope is, can we get the epsilon small enough and find just the right algorithms so that exponential in 1 over epsilon is more than we could imagine doing classically. And that's what the Google experiment and the recent experiment of our friends in China have demonstrated. They validated this prediction that if you harness quantum physics, you can get this exponentially powerful computing model. Right? And, moving further along, we're getting close to having quantum repeaters, right, which are small quantum computers that will enable a global quantum communication network, or at very least initially long distance, but ultimately we're looking for a global quantum communication network. And before we know it, we'll also have a fault-tolerant quantum computer. What sorts of practical applications? I've been pushing that rope for a long time. And, 6-7 years ago, we organized a great workshop in Toronto, and we probed this. And really talented people from all around the world were exploring this. And there is a core of the community that's been working hard on this for many years. But in the last 2 years, this exploration is starting to explode. And it's a convergence of two things. It's starting to become more interesting for the academics, for the researchers in the field to do it. Because if 10 years ago, they're really, compared to the rewards you'd get by doing more sort of academic research versus looking for applications of existing tools, there wasn't much reward in academia and there wasn't much reward in industry. And similarly for industry, why should we invest resources in finding applications of this computer that we don't even know when it will be here? But that's changing. So we're really seeing an inflection point and a mass proliferation of people looking at real-world applications of these quantum algorithmic tools. Such as, what does it mean for finance, right? We've undergone enough massive disruptions in the global financial sector. We don't want another one. So we want to know, how will this affect the financial markets in many different possible ways? Hopefully good ways, but even in advance, it might be good for some, but it'll disrupt others, right? So, and the uncertainty, even if the net gain is positive and that we're creating more value, just the uncertainty of suddenly an industry shifting from one part of the world to another entirely You might argue philosophically, well, on the whole, it's a good thing, but obviously it could have stability implications. So there's lots of reasons to understand how quantum computing advantage will impact the financial sector for stability reasons alone, as well as, of course, profitability. Part of understanding the impact is understanding, for example, in some cases, you might see a paper that says, with a classical computer, this would take 1 trillion years, and with a quantum computer, it would only take 1 billion years. So that doesn't sound like a practical implication, right? But of course, in some concrete examples, that 1 billion years became 1 year, and became a month, and became a few minutes, right? So how big of a quantum computer is needed is a quickly moving, that's a fast moving target, because it depends on so many things. At the high level, I could invent a better algorithm. That could be tremendously impactful. I can find better ways to implement that algorithm as a high level circuit. I can find better ways to compile those circuit components down to fault tolerant operations. I can find a better fault tolerant code. I can build a better device that's faster, lower errors, more connected, and so on. Improvements anywhere along this stack will reduce the amount of quantum resources needed to attain your solution, which means two things. You'll get it sooner and cheaper. And it's all moving in the one direction, right? We're just constantly finding better and cheaper ways to implement a given algorithm, and we're constantly inventing new algorithms. So you can't be stuck in what's the cost estimate of solving this problem today, because that's going to go down, right? So when you want to know, for example, when will a quantum computer break our crypto systems, you can't look at a 5-year-old paper and their cost estimates. You have to look at today's results and even extrapolate what might it look like in 5 years. So this is an illustrative document. Do not take any of these numbers as these are just illustrative numbers. So when you're trying to do an assessment, because you're hearing different types of quantum computers, and these people have 50 bits, but these people have 5,000. What's going on? And when are we going to break RSA? When are we going to have a useful quantum computer? What does useful mean? So there's many different facets to that question. So I break it up into 3 kinds of qubits. We already have annealing qubits. We're entering the era where the noise and control is noise is low enough, the control is high enough that we're in the NISQ era, which in a sense are higher quality, different in some sense, higher quality qubits than the annealing qubits, but for different purposes. And soon we'll reach the logical qubit era. And one logical qubit, roughly, very roughly speaking, could be on the order of 1,000 physical qubits. So that's why these timelines are sort of aligned like that. And if our estimates say it takes about 4,000 logical qubits to break RSA, and there's a good chance that'll happen by 2029, you can kind of work backwards. You say, but I don't want to break RSA. I want to do better arbitrage, or I want to design a better material. You can work backwards. And my algorithm only takes 100 logical qubits. You can at least come up with a partial ordering of how difficult these things are and gauge, well, we know this will happen before that. And we don't know any of these future events for certain, but we're starting to get a rough sense of what the relative likelihood is. And of course, we're in business, so we're always managing risk and uncertainty. But we at least want it to be informed decisions and informed estimates of what the risks are. One of the tools my team has developed, my early work, I got into this from an application perspective, which is breaking codes. So I got very interested in the algorithms that were relevant to breaking codes. Okay, so my application area was cryptanalysis, algorithms. We took Shor's algorithm, Kitaev's algorithms, we enhanced them, improved them, invented new methods. And then in the last decade or so, started focusing more and more on all the tools needed to take something like Shor's algorithm and compile it down to run on a realistic architecture with the fewest possible resources, and automating those tools. Because we're talking about thousands of qubits now, and we have powerful methods, but you can't do them by hand anymore. Right? So our company, one of my companies, works on these tools in the middle, right, connecting your application areas. We also offer services that help you make that connection. And then we have tools that really compile it down in a hardware agnostic way to run on a large suite of the available architectures. Which, just reminiscing, back in 1997, I did this whole thing, an artificial algorithm, the Deutsch algorithm, down to a cytosine molecule manually. You know, it was just literally talking to another person saying, what can you do with your spectrometer? How can you implement a Hadamard gate? And, you know, I listened and I said, okay, don't do that. I'm going to recompile the algorithm in terms of the pulses you can do most easily. Because we'll do it faster, we'll have lower noise. And we did that. So this is like 23 years, more than 23 years ago. We've come a long, long way in terms of countless more platforms, much better fidelities, more algorithms, and very sophisticated automated tools, and growing. We're constantly working on this and writing papers, us as well as colleagues all around the world. So that's the happy quantum side, right? But as I said, you know, one of the things we're optimizing is the resources needed to break RSA. And you know, I mentioned this timeline. All this happy stuff, for that, you know, if we break RSA, if we haven't fixed our cyber systems to be resilient to quantum attacks, the happy quantum, all that value being created by quantum computing technologies is at risk. Okay, and all sorts of very unfortunate and destructive things will happen if we have to suddenly put the brakes on quantum computing, creating value with quantum computing if it's a lethal weapon, basically, because our cyber systems, especially our critical systems, haven't been quantum proofed in time. There's other, so, right, because all our digital systems essentially depend on cryptography. Symmetric key cryptography, which we know will be weakened by quantum attacks. We have solutions that are resilient to known quantum attacks. You just use bigger keys with the existing algorithms. So easier said than done. Just ask a bank how long it took them to go from DES or AES to AES, or how long SHA-1 to SHA-2 took. So I don't want to take that for granted. But the really, really worrisome part is you can't just go to bigger key with RSA or ECC, right? Because there's no exponential gap between using the system and breaking it anymore, right? In the old days, you know, if you wanted more security, you would add a few bits of key, and that would make it twice as hard to cryptanalyze it. Just a few more, and it's 4 times. So just a handful of bits, and it's 1,000 times harder to break the code. But if you want to make it twice as hard to break RSA on a quantum computer, you need to almost essentially double your keys, your key lengths, actually more than double your key lengths for RSA. So, well, actually roughly double. You need to scale them linearly nowadays. So that's not a viable option, okay? Because you're making the work as hard for you as you are for the adversary. There's a tiny gap perhaps, but it's not big enough to be useful in practice, at least for more than buying you a few months, and the adversaries aren't going to be so kind as to tell you how well they've compiled their algorithms. So this really, every business, you know, in a critical sector, critical infrastructure, in the IT sector, needs to understand what this risk means to them. So we pioneered the quantum risk assessment, quantum risk management practice. This is an outline of our methodology here, and organizations around the world are implementing this, inventing their own twist on it, and applying it in their own specific sectors. This is following, for example, the NIST cybersecurity framework, but you can also align it with ISO or other risk management frameworks. This is the starting point, and your own results will guide your next steps. Right? Next steps include, of course, monitoring the technology, both the threat and the solution, trying solutions, proofs of concept, understanding the vendor landscape, and so on, and engaging with the relevant vendors in your supply chain. So we are, in the last few months, in the last year or two, things have really been ramping up. I think we're approaching 3 critical inflection points, 2 of them relatively soon, that will vastly accelerate the need to have our cyber systems be ready for quantum attacks. Okay, so the first part of my presentation, I've been talking about happy quantum, quantum software, applications, and so on. That's great. It's all under threat if we don't fix this one problem. We know how to fix it, so it's not a showstopper, but we have to actually do it. And it's no longer an after-dinner talk. Like, this really requires immediate action for critical sectors. It will impact you directly or indirectly. The first inflection point, the most definite one, is the NIST standardization of the new cryptographic post-quantum algorithms. That's due, they're going to start finalizing the list in 2022-23. and publish them in 2024. That's pretty soon. And I really think you better be 75% ready for the most part. Of course, it depends who you are, but and ready is mostly planning and testing. It's that last 10% that is really deployment, and people maybe focus on too much, but you're not going to be able to deploy quickly and deploy well if you haven't been planning for and got most of that work, the planning effort done in testing and validation, proofs of concept. So, and I really think you better be 75% ready when that happens. Because when that happens, that's an inflection point. Everyone who's just been doing the testing and the way, but hold on, don't deploy until you have a standard. I don't want a many people want a standardized algorithm. There's a strong preference for that. It might not be a requirement, but it's a preference. And if waiting one more year means I get a standardized algorithm versus, risking picking the wrong algorithm, many will wait. So there's a lot of organizations, vendors waiting for that standard. And then they're going to follow up on their next steps. So it'll be a great momentum push at that point. That's on the solution side. Many serious organizations will be accelerating on the solution side, and you need to figure out, what does that mean for me? Where am I? Do I need to upgrade to something after I just finished buying the old the old tools? Right? You want to integrate this in your technology life cycle. The next inflection point, again, the precise date is less certain, but it's that fault-tolerant logical qubit. That will make the threat ever more clear, okay? Because we've gotten the supremacy, we've gotten qubit, all the milestones along the way, which are very complicated and technical, and people didn't really know what to make of them. And then supremacy, so-called supremacy. With the logical qubit, I mean, that's really a starting gun to scaling these devices. Not to say that it's going to be easy, but you can't bet. I mean, there's a serious likelihood that it will just take a relatively small number of years to scale it to a point to be cryptographically relevant. So I really think by the time that fault-tolerant qubit comes, if you can't demonstrate to your stakeholders, like, what you want to be able to say is, oh, that's lovely. Isn't that great? We'll have all these positive quantum applications. We're ahead of schedule in our quantum, cyber readiness plan. Basically, we can just continue, or we're now ready to enter that next phase. But it's calm, cool, collected, because you've already got the 90% preparation done. Of course, you're continually updating this plan based on any new developments. But by the time that fault-tolerant qubit is demonstrated, I really think major vendors, critical sectors really need to have demonstrated. They don't necessarily have to have deployed all these solutions, but they better have it well in hand, where it's really an implementation issue, not a design issue, or what does quantum mean issue. Another inflection point, which I think will be a short number of years after, is we're going to have a greater availability of commercial long-distance quantum key distribution, which will vastly enhance our ability to protect our cyber systems against the systemic threat of cryptanalysis. Okay, so I'll talk a little bit more about this one. And I see this as an addition to so-called post-quantum cryptography. And, are you going to be ready for that? You're going to be ready to benefit from that additional resilience. So how urgent is all this? The timeline's a little different than it is for the so-called happy quantum, right? Because a lot of our information has a long shelf life. Let's call that X years. We have it takes Y years, say the migration time. It takes some number of years to migrate to these new systems. Again, ask the banks how long it took to migrate from DES to AES, which in comparison is trivial compared to what we have to do now. And even if they wanted to do it faster, they could have done it faster, but there's only so fast they could have gone. For something as trivial as replacing, again, logically trivial, I know in practice it was hard, one cipher with another one. So there's a long migration time. We've chopped a few years off of that because of all the work that's been done, but there's still a long migration time, Y years. At the end of those Y years, you're supposed to provide X years of confidentiality. But if Y plus X is greater than Z, you won't. Right? Those encryptions at the end of those Y years will be vulnerable in less than X years to quantum attacks, quantum cryptanalysis. For any adversary that records that information or gets access to recordings of that information, they in principle, they have the ability to decrypt it and exploit it in whatever way cyber criminals or state actors choose to exploit that kind of information at that point in the future. And if you're following cybercrime, you realize it's getting increasingly sophisticated, specialized segment. It's a business. It's a collection of businesses. Everyone does what they're good at. So this naive notion that, oh, but the threat actors who own quantum computers won't come after me, that's not how it's going to work, right? You don't have to own the quantum computer. You need to hack into a quantum computer or get access to it. You break the codes, but then use those private keys to offer some other criminal service, which offers some other criminal service, right? I don't know exactly how they're going to structure their businesses, but it's naive to think it's one actor that is going to have the quantum computer, use it to find keys and attack individual targets. As we see today, you have people who write malware that gets sold to people who use it to create botnets, and the botnets are used by other people to do denial of service attacks for the paying customer. So there's already 4 levels there. So we don't know how cybercrime will unfold, but it's certainly only going to get more sophisticated. So what is Z? I've talked about the timeline for a fault-tolerant qubit, and I've been estimating Z since the 1990s. And in 1996, when I was in England, I said at my master's exam at Oxford, not for 20 years. So 0% chance in 20 years. It will happen, but not in 20 years. In 20 years, I'll have about 20 qubits, and then it'll be clear. And my 20-year probability went from 0% to 1% to 10% to now more than 80%. And I don't even talk about 20 years anymore, right? I think last year I said a 20% chance in 10 years. And so much has happened in the last year that obviously the odds went up and the timeline is going down, right? But I'll issue a new update in 2021. And you don't have to take just my word for it. Again, with the Global Risk Institute, we'll have the updated timeline coming out in early January. But this is what 22 thought leaders last year said. My own estimates are somewhere, in the middle of the pack. But you can look at it. It's already non-negligible in 5 years, right? For a critical system, for our digital economy, especially in a short number of years. Remember, look, I'll get to this soon, but the stakes have obviously been going up and continue to go up. So even a 1% risk is too much for some. Certainly 20% is too much for most. And not long after, again, we don't know exactly, but given the time it takes, this is not a weekend patch, right? It takes many years to prepare this. If you rush, you'll make other mistakes that adversaries without quantum computers can capitalize on. So you absolutely do not want to rush rebuilding the foundations of your cyber systems. The solutions, well, the obvious one is to replace the current mathematical codes with new mathematical codes that can't be broken by quantum attacks. Easier said than done. First of all, we never know for sure if they can't be broken. Key agreement, public key-based key agreement is hard. There's extra mathematical structure. It's harder than an encryption algorithm or a hash algorithm or even a digital signature, which really fundamentally just needs a one-way function. Key agreement needs special mathematical structure. The vast majority of ideas that have been thrown at it have been broken. There's only 4 possibilities we know of that can't be broken by the known quantum attacks. Okay, so that's where we are. The beauty of post-quantum cryptography is you don't need a quantum computer to implement it. You're designed to resist quantum attacks at a high level. It's a plug-in replacement for what we have. So that's a great effort going on worldwide. In addition to that, we can also do more than reestablish the status quo. We can achieve quantum cryptography, whether it's quantum random number generators or quantum key agreement. And these are not at war with each other. Quantum cryptography is an additional tool in our ecosystem, which gives us an extra layer of defense in depth. Right? It's a great addition to post-quantum cryptography. And you can act now. You don't need to. People say, well, it's just not available yet. It's available. There's strong open source platforms. There's commercial platforms. You can start testing and planning now. You can even deploy now. If your risk analysis says we really need to protect these communications today, you can deploy these things today. We offer commercial support for this. There's proprietary vendors. We don't suggest replacing your current methodologies with this. We suggest augmenting them. So that way you keep your current certifications, whether it's FIPS 140-2, PCI, whatever it is, keep those, layer this in. It's available right now. Right? We've done things with, major, IT vendors around the world, such as HSMs. The other point I want to make is with regards to quantum cryptography. It's often, dismissed, which I think is a mistake. We don't get to retool our cryptographic foundations very often. This first of all, and I'll make some other points later. But another important point, one point I want to make with this slide is, physicists and scientists will build a quantum internet. Right? By quantum internet, I mean a global scale quantum communication network, which, among other things, can enable global distance quantum cryptography. They're going to do that. Okay, they're not asking permission. They're going to do it. And our job as security specialists, I'm putting my security hat on versus my quantum hat, is how do we leverage this amazing new tool, this amazing new capability to help make our cyber systems more resilient? I try to use the word resilience more, because security and resilience are actually very different things at a certain level. And really, what world really needs now, in addition to more security, because there's an obvious case for security against today's attacks, is greater resilience. Right? As we experienced with COVID-19, it'd have been nice if we'd been more resilient. We could have been less resilient, so I'm not ungrateful for the readiness levels we did have, but we could have been a lot more ready and handled this a lot better. So this global telecommunication network, quantum communication network, is going to happen. Our job is to figure out how do we use it to make our systems more secure. All right, and it's a risk versus convenience trade-off that security specialists need to make. And the risk is going to change, the convenience is going to change, so it's something you need to continually track. Don't make a decision today in 2020 that will rule out options for people in 2025 and 2030. Right? At the very least, leave that agility in there. Design this option in. And we develop a 4-layer architecture. We're standardizing the interfaces. We have open source options for proofs of concept, and we're developing commercial grade versions of this as well if you really want to deploy it in a real world system. We're working, for example, with the Canadian Space Agency and others around the world to design real world implementations of this. So just to wrap up, this quantum threat business may look like, a terrible nuisance, right? This is a great misfortune, but we're going to have to deal with it anyway. But I think that's probably wrong, because security specialists have been concerned. Look, in the 90s, if you say what would have gone wrong if people figured out how to break RSA in the 90s, only a few people could give you real examples of what would have gone wrong, right? Some fax machines, some fax communications were ECC encrypted. Really important faxes were ECC encrypted, right? Of course, nowadays, if you're a bit younger than me, you're asking, what's a fax machine? So, it wouldn't have been catastrophic. The digital economy would not have collapsed, right? So the foundation wasn't great, but a lot of our colleagues and friends, like Taher El-Gamal, the inventor of SSL, he thinks our current cryptographic foundation lacks cryptographic agility. If a smart mathematician figures out how to break RSA, which could happen any day, could have happened in the last 40 years, major advances did happen, but we were able to pivot quickly for those. But there could be a catastrophic break. We don't have the ability to pivot quickly enough for anything beyond going to a bigger key, provided you give us several years notice, right? So the lack of cryptographic agility and the lack of defense in depth at the cryptographic foundation has always bothered people. But, who cares? The stakes are low, except now they're not, right? The same foundations, which are already, not perfect, but maybe good enough for the 90s, are now being used in 2020, protecting everything. IoT, it's not just information, it's things. And what are they going to be protecting? So I guess the point I want to make is the transition to post-quantum is forcing us to rebuild the foundations. So we're not just going to reestablish the status quo and go from going to bed at night terrified that somebody figures out how to factor numbers to going to bed at night terrified that somebody figures out how to find short vectors in a lattice, because that nightmare kind of feels the same, right? It's just a different math problem. So we're doing more than just reestablishing that status quo. We're rebuilding it more robust. We're going to enable hybrid key agreement, so you can combine 2 or more algorithms. So not only does somebody doesn't have to just break one code, they have to break 2 or more of them. And if somebody does break them, and let's say you have time, you have agility, you can very quickly bring in a code that hasn't been broken if you're not using it already. So that agility and hybrid and post-quantum, so you're designed already to resist quantum attacks, known quantum attacks, will actually make us much better and a little more appropriate for given what we're putting at stake here. The designers of the internet did not imagine, embedded technology in our brains and our hearts and so on that could threaten our lives if they're hacked. That the internet would be protecting those, they'd be relying on the internet. So these things were not designed with the stakes we're putting on them. What's going to be dependent on our IT infrastructure in 5, 10, 20 years? So we need to build an even more robust infrastructure. And that's what QKD is one of the tools. It's not the only tool, but at the least, it protects against the catastrophic failure that would be caused by an unexpected cryptanalytic advance. So I really think from a side, my background's in cryptography, quantum computing, I hated it. I thought it was the dumbest thing I'd ever heard of. I didn't want to deal with it. Then I realized I was wrong. In hindsight, it's a blessing in disguise because it's forcing us to do what we know is good for us, which is create a more robust foundation for our digital lives. So in closing, I want to go through, this is not, a neat entertainment topic. This is actually, there's things that need to get done by many sectors. So I think every company, company in the critical sector, a bank, IT provider, government departments, they have to, if they haven't already, put somebody in charge of producing your quantum readiness plan in 6 months. Okay, they have to be in charge. This is not just watch a few YouTube videos anymore. Somebody has to be in charge and accountable. But of course, you make them accountable, you have to give them the support to succeed. They don't need a huge budget initially. Again, if you've already done this, great. I have other resolutions for you. But they need broad executive support. You can't have one person in one department of a bank in charge of the quantum readiness plan and the other 10 departments they need to talk to ignore him or her, right? So they really need high-level executive support. And, probably someone from a risk department, but realistically, they need to work across departments, right? So you need, it almost doesn't matter. You need somebody who gets stuff done, okay, who knows how to work across different departments and different cultures. Because the C-suite always says, love my CISO, don't know what the hell they're talking about. Like they don't know how to talk in business terms. And I apologize to all my CISO friends, but this is what they say about you behind your back. So we need people who can communicate in business terms across the different silos of the various organizations. The other thing, as you start doing your quantum readiness planning, do your risk assessment, start engaging the relevant people in your ecosystem. Okay, it could be standards bodies. Give them feedback. You want to make sure what they standardize meets your needs. You might realize there's standards that you're going to need that are not even on anyone's roadmap. You want to identify this sooner. So among others, engage people in your community, especially standards organizations, because standards play a really important role in cybersecurity. So we want to make sure the standards are ready. Not just the technical standards. What about the risk management standards, right? And what are the auditors doing with this? And so on. And very low-hanging fruit. Once you have a clue of kind of sort of where you're going, you can, within 12 months, start. Another way to engage your ecosystem is to engage the vendors in your supply chain, right? Update the RFPs. I can suggest language to you that won't annoy them too much, but initially the language is just going to be informative. Do you have a quantum readiness plan? What is it, right? And it's slow. You're going to turn up the dial over time, because at some point you're going to realize, hey, we need our connections to our cloud to be quantum safe by 2025. Right? We've done our internal risk assessment. We need to do that. So you better be talking to your cloud vendors before, December 31st, 2024, if you want that done for 2025. That's a long conversation. And you can't just not mention this topic year after year and then suddenly say we want this next year or in 2 years. They need to get this on their technology roadmaps. And honestly, many of these vendors, they say, yeah, we get it, but our customers aren't asking. So start talking to them and just at least start aligning your roadmaps, what you need and what their product roadmap looks like. So that's the last thing I wanted to say. The last bit of homework is, engage your vendors and ask them for what their quantum readiness plan is. So everyone in this ecosystem can, align where they need to align and be ready in time for each other. So thanks very much for your attention. I really look forward to the discussion and questions.
Thank you. Please do put the questions in the chat. We'll try to answer as many as possible. And I may want to start with something from David from the chat. It's a bit of a provocative question. I'm playing devil's advocate here. If I'm a small, medium enterprise, do I really need to worry? Is it not just, Amazon or Google or Microsoft coming to me in a couple of years' time saying, oh, here's your quantum readiness kit. You just switch it on, job done.
I mean, SMEs are a serious issue in cybersecurity, not just quantum, all of cybersecurity. And governments around the world are trying to figure out what to do about it. Because on the one hand, they're the weak link, right? In many, many cases. On the other hand, they don't have the resources they don't have the maturity of a bank or the resources of a bank. So ecosystems need to work together to figure out how do we help the SME market. And the obvious, some of the obvious answers we hear, of course, is, well, they should be using cloud, focus on identity, 3 simple things. So it's harder for you to screw things up, so to speak. So in terms of this, most of it hopefully will be resolved by your vendors, but it's a good idea to start asking them, because the more of their customers they get asking this question, the more of a business case they have to actually start incorporating this into their products. So the answer may be yes, and I'm not advocating you do anything like in the doing side, right? But you should figure that out for yourself, right? It's worth more than just a 1-hour talk to figure out. Let's just do that. The person you put in charge might come back to you in 6 months and say, yeah, I think we got it under control because, our 365, we're just going to make sure Microsoft has it, we don't have we don't deal with long-term information, or if we do, you know what, we're ready to absorb that risk. So it doesn't have to be a massive undertaking for an SME to figure out its vulnerabilities. And then, if you do find something that really is potentially catastrophic, and look, if, regulators are going to suddenly in a year or two introduce regulation that you're not ready to comply with, that could be detrimental, right? So you want to at least be aware of whether that hypothesis is correct or not. But I think there's already, again, it might be where you just deal with your vendors, and that's fine. It really depends on the nature of your business.
Thank you. A slightly related question like this comes from Paolo. So you said it's important to have someone in charge of your quantum readiness. What kind of person would it be? Is it a tech person, a risk person, a mix of the two? You said it should be someone be able to speak with the business. Can you give us a bit more around that? Who will be the ideal person?
So it's all of the above, and of course, no one will have all of those skills. So I really think they have to have enough of an understanding of the tech, right? But they also have to so you need somebody who straddles the tech and the business side of the business, and they could be from one or the other. Like I have one colleague in a big Canadian bank. He comes from audit, right? CS background, was in audit, and now he's he's moving around. So he knows many of the silos. He understands the nature of the beast, and he's a good communicator. So I think partly it's personality. They do have to have a basic understanding of the technology, but honestly, it's not rocket science. So you need somebody who's comfortable enough. They don't need to understand the math underlying the algorithms. They don't need to understand quantum physics. Like it's really as simple as I presented it here today. So part of it is mindset and people skills and the ability to understand business and enough of the technology to be able to Again, they don't have to do everything. They need to sort of coordinate, ask the questions, co-opt, help as they need it.
There was another one related to what you touched before about government setting the standards. Can you elaborate a bit more on what are governments doing about this? Enough, not enough?
The positive things they've been doing. So, for one, the U.S. government deserves credit for one, the NSA, when they announced in 2015 that they're switching to quantum resistant algorithms, that was a great service to the whole global community, because it drew attention to this, right? And then it's, of course, set the NIST standardization process in place, which is really focused. It's a massive, it's hope for humanity, in that researchers from all around the world are working together to try to, in the open, to try to develop a small set of strong algorithms, right? So that's an amazing thing that deserves credit. So that's a very low-level technical standard. ETSI in Europe, based in France, where they do global standards, has, even before this, was working in quantum cryptography standards. I started hosting this ETSI IQC workshop in quantum safe crypto, and they've spun out. They have two standards group working in this space, producing a wide range of standards, informative standards, and so on. Standards for quantum cryptography, for example. So you can design now to integrate QKD keys into your software systems, even if the hardware isn't even there. You can design it in. So it's an option, and if the hardware becomes available as a service, say, great, I'll just flip that switch, right? So ETSI's been doing great work. ISO, ITU, they're developing all sorts of IEEE is now starting a group on risk management standards. X9 has been exploring the financial standard, has been exploring this for several years now, at least a couple of years. Well, not their industry, but so government has many, many roles in this, right? We say government, but government as a customer of technology needs to do the RFP thing. They need to change their procurement guidelines to start asking at least strategic questions. Eventually it'll be requirements, but they need to start doing that more than they currently are. Some governments are, and I applaud them. Most aren't. And that's government as a customer. Government as a regulator needs to start asking these questions a little more, okay? Light touch, but start the conversation. And there's been positive steps. The overseer of the Canadian financial sector recently published a consultation paper which asked this question. So that sends a very good signal and is starting to start the dialogue, right? So very positive steps. We need to see more of that around the world. So as a customer, as a regulator, as a funder of technology, this should be aligned with its cyber strategies, and so on. So there's many roles for government to play here. And around the world, you'll see pieces of it happening. I think we just need to start doing that more and maybe sharing best practices around the globe. I mean, the other thing, for cyber, the role government, when there's an externality to the model, you can't have a world of privatized gains and socialized losses, right? I mean, capitalism doesn't work when you only privatize the winnings and not the losses. And government has to, for something abstract like cyber risk, there is a regulatory element to making sure these risks are properly accounted for. I don't believe in prescriptive, regulation. The role of regulation shouldn't be to have somebody tick a box and absolve themselves of responsibility. That's not the kind of regulation I mean. But there are, and I use regulation in the broad sense of creating proper accounting of these risks and accountability for the risks. So we're not socializing the losses.
Thank you. Michele, there's some echo there. So Ray mentioned, or Ray referred to the Global Risk Institute Quantum Threat Timeline and asked when there was an update. Now, I think I heard you mention that there would be an update on some of that particular data at the beginning of next year. Is there a plan for a broader update, or what's the timeline on that? Because clearly it's changing so fast.
It's a new report. We asked most of the same questions plus some additional questions, and that'll be just before Christmas. We decided not to post it, so we're going to post it in January. and then we'll do the other. There'll be the next iteration next autumn. So the idea is to do them once a year.
Excellent. That makes sense. You've touched obviously a little bit on the geopolitics of this, but it would be good to get your view as to overall, ultimately, from a nation state point of view. Obviously, there's the good guys versus the bad guys in terms of criminals, but from a nation state point of view, is this overall a collaborative journey, or is this sort of the new space race?
Parts of the quantum. So for quantum safe, I think it needs to be a collaborative journey. I don't. Of course, we're everybody wants to have the biggest piece of the solution pie, but overall, we definitely need to agree on the standards and moving together as an ecosystem, because interoperability is critical here, and trust across all these platforms is critical here. So I think on that side, it's more of a collaborative thing. On quantum computing technology, harder to predict. Harder to predict exactly how it'll unfold. Like right now, my hope is, there of course is going to be competition, but let's have this great value creating capability of quantum computing be a resource that's available at reasonable cost across the planet. And where the competition is going to be is on top of that with the various applications and so on. That's where I hope we're heading, instead of literally having only these people have access to quantum computers and the rest of the world doesn't. I think that would be bad for humanity. I think we want to be competing at one level above that.
Yeah. And I guess to that point, then, most people will be getting their quantum computing access as a service via the cloud rather than owning their own. Are we going to end up in a situation where the regulator will expect the likes of IBM and D-Wave and the other hardware producers to somehow regulate the algorithms that are running to make sure that the bad guys are not decrypting things appropriately?
That would be a terrible scenario, first of all. And we can avoid it. Like, we can avoid that dystopian thing you just described, which won't work, by the way. And it just, another self-inflicted wound on humanity, right? We can avoid that by just deploying quantum safe cryptography robustly around the world. So there really is, that just doesn't exist except the niches that are not worth worrying about. When you focus on the value to be created, you're not going to be so worried about some obscure system that is not critical. If somebody's going to go after some Windows 95 type outdated system that doesn't protect much. So I think we can take that scenario off the table, but we have to choose that. If we don't, we will enter this dystopian situation where, wait a minute, now we got to slam the brakes on, and we're going to start adding these completely unenforceable regulations on vendors. And there's many different shades of stupid there, and they're all bad. So I think we really want to avoid that scenario. But it's a great question, and it's just another reason that quantum safe crypto is critical if you want to benefit from the positive applications of quantum computers.
Perfect. Okay, thank you for that. We targeted wrapping up in the hour, so that gives me 30 seconds or so really to just thank you and share a few points with the community. So as some people are aware, Michele, reading some of your comments in the IET, that's the Institute for Electronics and Technology magazine back in April 2019, was part of what helped me on this journey. So it's fantastic being able to hear from you and speak to you after, I guess, almost 2 years now from having read that. Thank you for sharing your thoughts. I think it's incredible how fast it's moved. You mentioned that you talked about it already in 1996. So you've obviously been on a fantastic journey, and we appreciate you sharing that. And we look forward to maybe having you back in a year or two when things have moved even further ahead. So thank you for that. Just to wrap up the community, thank you all again for the input you're giving us, for suggesting speakers and things. We have a Quantum Stammtisch event on Monday part of what we'll do is we'll discuss the points we covered here. And then on Tuesday, the 12th of January, we have an event around patent protection for quantum hardware, software, and algorithms. So that should bring an interesting new angle with 2 patent attorneys who are talking about that. So that's available to sign up. So really all it remains to say, Michele, thank you once again for your time, your insight. Best wishes for the holiday period, and we look forward to talking to you in 2021. Thank you very much.
Thanks so much.
Goodbye.